Hello, welcome to this video which will be about chemical vapor deposition CVD and atomic layer deposition ALD. Okay, so let's begin with a non-technical summary. So when building up a semiconductor device, right, normally we have to build many layers, right, especially in the back end of life. So you see here all of these metal layers are being layered one above each other for the back end of the chip. And so to do that, we need to find a way to deposit material, right, sequentially so as to build up this structure. And one of the way to do it is via a chemical reaction, right? So it is very similar in principle to the chemical reactions that you are used to in the school laboratory last time, where you mix two chemicals and you get a resultant product. However, the difference is that now in this case the chemical reaction is happening on a surface, right? It's happening on a surface, and so this is the principle behind CVD, chemical vapor deposition. Okay, so let's dive straight into the content. So here you can see a common setup for atmospheric pressure CVD, also known as AP CVD setup. So we see that we are pumping in your reactant gases into the chamber, and the chamber itself is heated up, right, by these heating coils, but the wafers itself is placed on a platform such that it is at a slightly so that it is basically exposed rather to your gases that's incoming into your chamber. So an example is that let's say you want to grow silicon, right, through a CVD setup. You can simply pump in silane, and silane can decompose into silicon and hydrogen gas. However, also in other setups, right, you may want to pump in certain dopant gases, right, to dope your silicon that's being CVD deposited on your wafer. Okay, so for AP CVD setups, right, it is operated at atmospheric pressure. However, because of certain reasons I'll go into later, it's actually not so common to operate CVD setups at atmospheric pressure, and nowadays we prefer lower pressures instead. And so what we normally do is that we don't just pump in the reactant gas, we also pump in diluent, inert diluent gas such as hydrogen or argon. Okay, so what is the mechanism of CVD growth? So actually the mechanism is quite similar to a lot of like surface control reactions that you may have seen before, right? Basically surface based chemistry. So the first step is you need to transport your material, right? So in this case is your reactant molecules, right, through the gaseous phase, right, via diffusion to the wafer surface, right, to your wafer surface. And subsequently there will be an adsorption step where your molecules are then adsorbed onto the wafer surface. And subsequently, once your two reactant molecules, two kinds of reactant molecules, in the case where there are two or more reactant species, they will then undergo a chemical reaction. And in the case of basically the deposition of silicon from silane earlier, right, it's just a simple decomposition of silane to get your silicon material. So because these molecules are adsorbed on the wafer surface, so there can also be a surface migration, right, surface diffusion, to allow the formation of basically a uniform layer, smooth uniform layer, and in certain cases, right, epitaxial growth can be achieved. Okay. So finally, if there's any byproducts, for example, let's say you're decomposing silane, your byproducts will be a hydrogen gas. It will be dissolved from the surface, and the diffusion away of these reaction byproducts from the surface. Okay, so what is the dynamics? What are the equations that can describe the dynamics of a CVD growth process? So we can consider two fluxes that occur in the CVD growth process. So the first flux is the flux of reactants from the gas phase to the surface. So this is simply a diffusion process, a gas phase diffusion process, which is governed by this kind of fixed law relationship. Okay, so we can see that it is proportional to somehow the concentration gradient, right? Concentration gradient, your difference in concentration, right, divided by your thickness of your diffusion layer term, this delta term over here. And the second flux is basically a chemical reaction flux. So it can be governed by this kind of a first order rate equation, where your Ks is a surface reaction rate constant. So in the steady state, right, we can equate these two fluxes together and we can obtain an expression for your CS, which is your rate of consumption of reactants at your silicon surface. And so we can translate that into the growth rate of the film, right, by dividing your flux by your basically your number of atoms per unit volume in your film that is being grown. So that what you get is you get a term that has units of basically like centimeters or like micrometers or nanometers per unit time, right? So we have basically a kind of z-axis kind of growth rate term, right? So yeah, and what we get is that we get a term that looks like this, a bit complicated term, right, which features both your mass transfer coefficient, which is related to your diffusion constant and diffusion coefficient, as well as your reaction rate constant, right? So it's a very complicated term, but we can simplify this into two regimes, right? If we look at this equation here, what happens if your Ks, your surface reaction rate constant, is much smaller than your, let's say, your mass transport coefficient? Then we realize that this term below can be approximated to simply Hg, which cancels with the Hg above, such that only Ks remain. So we see that this, in this case, it can be approximated to be only varying with respect to your surface reaction rate constant. So you can call this a surface reaction control case. And so how do we make sense of this, right? We can make intuitive sense of this by thinking that if your mass transport coefficient is much greater, that means your diffusion step occurs very fast. Then what is the rate determining step here? The rate determining step is your surface reaction, right? So the overall rate of growth only depends, or approximately only depends, on your surface reaction rate. However, in the converse case, right, when your surface rate constant, surface reaction rate constant is much greater than your mass transport coefficient, right? So you see the term below approximates to just Ks, which cancels out with the Ks in the numerator, right? And therefore the eventual equation only has Hg. So the rate of deposition only depends, or approximately only depends, on your mass transfer coefficient. So how do you make sense of this, right? Once again, we consider that the surface reaction is now the one that occurs very quickly. So what is the rate determining step? The rate determining step is the mass transfer step, is the diffusion step. And so therefore the overall deposition rate, right, is dependent on your mass transfer rate. So we can also kind of plot this, right, visualize these two regimes with respect to temperature by plotting the deposition rate in a log scale against your temperature. So why do we do the log scale, right? That's because your surface reaction rate constant follows an Arrhenius relationship with respect to temperature. So of course, Arrhenius relationship refers to this kind of formula, right? This kind of relationship over here. So we realize that if we plot the log of the rate against 1 over t, we can get the straight line for this regime. So we see two regimes, right? Two general regimes. It's the same as that seen earlier. At low temperatures, right? When 1 over t is high, is a low temperature. Low temperature means that the reaction rate occurs slowly, right? Reaction rate occurs slowly. And therefore, this regime is a surface reaction controlled regime, because the surface reaction becomes the rate determining step. However, at higher temperatures, right, surface reaction can occur very quickly without any problem, and so therefore we enter the mass transfer control regime, where the diffusion rate is the one that determines the eventual rate of your thin film deposition. Okay, so which regime do we want to operate in? Okay, we want to operate in actually the surface reaction control regime. So why is this the case? Okay, let's consider the case where we operate in the mass transfer control regime, right? We see that the deposition rate occurs very quickly, right? So that's extremely good. However, there's a problem, is that when the reaction, or when the overall process is dependent on the mass transfer rates, we see that the overall process becomes highly dependent on your flow rate of your gases, because that is what determines your mass transfer rates, right? And so this is not desirable, because actually it's more difficult than it sounds to control the flow rates of gases in a three-dimensional chamber, right? So the result is that there could be poor uniformity across the wafer, right, between wafers, between batches. Okay, so we actually want to operate within the surface reaction control regime, right, where your gas flow rate in, like, let's say one end of the chamber versus the other end of the chamber, or in one batch versus another batch, does not really influence the overall growth rate. What determines the overall growth rate is the surface reaction, right, which is a function of temperature, which is more easily controlled, right? We can have certain uniform heating elements below the wafer and things like that. Okay, so however, of course, we see that the compromise is has to be accepted, because the growth rate will be lower. Okay, so how do we mitigate this? How do we mitigate this? You can actually use a low pressure CVD. So when you have a low pressure CVD, turns out what happens is that the mass transport coefficient gets increased, because you can think of it this way: when the pressure is lower, right, the flow of your reactant gases is not so hindered by your other, let's say, diluent gases or your other gaseous species. Diffusion, and therefore mass transport coefficient, right, is enhanced, is increased. So you can see a upwards translation of the curve in the mass transport regime case. And so what we see is that the boundary between the mass transport regime and the surface control regime, right, shifts to the left, which means shifts to lower 1 over T, which means shift to higher temperatures. So we can use higher temperatures to achieve our deposition and still remain in the surface reaction control regime. That means we can actually attain higher deposition rates at these higher temperatures, while still remaining in the surface reaction control regime, which is a desired regime that you want to operate in. So that is why normally we see that in the real industry, we see things like low pressure CVD, we see things like sub-atmospheric pressure CVD, so it's like below that of atmospheric pressure, but we rarely see atmospheric pressure CVD anymore. Okay? So common CVD processes that can be done, right, they're often done in industry, semiconductor industry, is let's say deposition of a polysilicon. So it is can be done through the decomposition of silane, and when you pump in gases containing your dopant atoms like phosphorus or boron, you can achieve a doped polysilicon, right, which is necessary to ensure your polysilicon is sufficiently conductive to use as certain electrodes. So one kind of feature that we always take note of in CVD processes is the resultant stress of the film, right? So depending on the deposition conditions, we can get either compressive stress or tensile stress. So compressive stress is the case where the deposited film likes to expand, so it compresses the silicon below, and that could cause cracking. And tensile stress is when the film being deposited likes to shrink, and so it causes tensile stress in the silicon below, right? And this could cause a wrinkling. So basically, if your stress is too high, it's not good for uniform deposition. Okay. Another kind of material that's often deposited is your silicon dioxide, right? It's often used as an intermetal or interlayer dielectric. So it can be achieved through the reaction of silane with oxygen. It can also be achieved through the reaction of basically a dichlorosilane with your N2O gas, right? So in the second case, actually, we are able to obtain a better quality oxide being deposited at a higher temperature. So the third kind of material that's commonly deposited with CVD is your nitride, your silicon nitride. Okay. So why I wrote SIN, not like the official or the proper Si3N4, is because by tuning the ratio, the stoichiometric ratio of your two gases, you can actually get non-stoichiometric, basically your SINX, right, where X can be a non-integer value, or not basically a nice ratio, right? So we can do that to obtain certain desirable properties of the nitride. Okay. So what is also actually quite common is plasma enhanced CVD. So remember the driving force, right, of CVD reaction in the previous cases was temperature. So the heat provided by heating coil drives the chemical reaction. However, sometimes that is not desirable because let's say you have your certain low melting point metals, right? Lower melting point metals like your aluminium or whatever, or maybe you need to balance out your thermal budget because you don't want too much diffusion to occur in your device layers, right, in the front end. So in this case, in plasma enhanced CVD, we use plasma to provide the energy for chemical reactions, right? Because remember, in the plasma, your species are ionized, they are higher in energy, they have a certain energy involved, even though overall, let's say in the macroscopic scale, the chamber can be held at a lower temperature. So the plasma system can be similar to your reactive ion etching, and then however, the problem is that in this case your deposition rate becomes more difficult to control, it becomes more mass transport dominated, and the quality of your film is normally degraded because you can think of it this way: at a lower temperature it's harder to basically arrive at your thermodynamic equilibrium of your material, which is of course a case where you have a nice crystal structure, low point defects, etc., etc., right? So, and your ratio of your resultant material is often non-stoichiometric, or once again, it's harder to fall into your overall thermodynamic energy minimum of your material. And once again, as mentioned earlier in the etch topic, right, a plasma can be set up in an inductively coupled plasma setup. So where your plasma is excited by a coil that is like away from your wafer, right? And you can see that we can do it in such a way that ions are now accelerated to the wafer surface for your reaction to occur. So let's say you are producing SiO2. So your oxygen ions and radicals, right, your ions actually are accelerated by the bias, by the voltage potential difference to your wafer surface, where your let's say oxygen ions react with your silane to form SiO2. So why is it good to have this kind of ion acceleration? Because this can allow for directional flux, which enhances deposition rate and also allows for the filling into deeper trenches. So imagine you have a deep trench, right, and if you have this directional flux of your species, it's easier to fill up the bottom of your trench, right? And also the phenomenon of this ion bombardment can help to make your film denser, right? Denser. So it's sometimes good if you want a more denser kind of film. Okay. Then as mentioned earlier, right, we want to deposit generally at lower temperatures. So recently, actually not really recently, but generally there's this trend to use thermally unstable gas precursors to allow for deposition to occur at lower temperatures. So basically, lower temperatures are sufficient to overcome the activation energy of the reaction because the precursors themselves are not very thermodynamically stable. So an example is this tetraethyl autosilicate. So in a sense, you can think of it as like four like ethoxy kind of groups bonded to your central silicon atom. And so this is actually very commonly used nowadays to deposit your silicon dioxide. Okay. And in addition, right, when you want to deposit your compound semiconductors, like your group 3, group 5 materials, like your gallium arsenide, right, MOCVD is often used, right? So we have a precursor of gallium, basically gallium kind of organometallic gallium kind of precursor, and your arsine, which is basically your ASH3, that can undergo this chemical reaction to form gallium arsenide and release your methane gas. Okay, and now I will cover the last technique in this video, which is atomic layer deposition. So atomic layer deposition is actually very similar to CVD in the sense that there is a chemical reaction that's happening. However, instead of pumping the two reactant gases onto your wafer surface at the same time, we pump in the precursors separately and isolate them through chamber purging. And so the reason for this is we want each step to be self-limiting, surface limiting, and thus allow for control of single atomic layer. So what do I mean? Let's say in the first step we flow your aluminum containing precursor. So we want to deposit aluminum oxide in this case. So in the first step we flow in your aluminum containing precursor. Then we only allow let's say one layer of molecules to be adsorbed on your wafer surface. And so this adsorption occurs by binding of your TMAL, your aluminum precursor, with your, let's say, your OH groups, your hydroxyl groups on your wafer surface. Then after that, we purge the chamber with an inert gas like argon to ensure that only this one layer of adsorbed precursor remains. Then we flow oxygen gas in, which is a second reagent, second reactant, and it reacts with the single layer of TMA adsorbed on your wafer surface to form a single layer of Al2O3, right, of aluminum oxide. Then we purge the chamber again to get rid of the remaining H2O that hasn't reacted, and then we pump in your TMAL again to get the next layer of adsorbed TMAL. Then we purge the chamber again to remove your excess TMA. Then we pump in H2O again to form the second layer of aluminum oxide, and then this process is repeated to get layer by layer deposition. So illustration is shown over here. So let's say imagine this is your TMA lah. Then you pump in your TMA, then you purge with argon, then you pump in your water, your steam, your H2O gas, then you purge with argon, and so this process is repeated. So at every time after your H2O feed, right, a new atomic layer of your aluminum oxide is deposited. And so it's important that we choose the right temperature window for ALD. We want to choose a temperature window where your deposition rate is independent of temperature. Right? It should be independent of temperature. It should be dependent only on the number of cycles that occurred, right? Because only after the cycle of the two gases will one new layer, atomic layer, be deposited. So in the ideal operation principle of ALD, the deposition rate should be independent of temperature completely. So we want to choose the window where that is the case. If we choose a lower temperature, right, there could be a dependence of growth rate on temperature. For example, there could be increasing relationship, right? As temperature increases, growth rate increases. Why? Because this temperature regime is so low that there's insufficient energy, right, for the reaction to occur to completion, right? So if you increase the temperature, there's still increasing deposition rate because the reaction has insufficient energy to go to completion, right? And if you choose too high temperatures, right, you can have the case where your growth rate increases as temperature increases because there starts to be decomposition, side reactions happening. Or it could be the case where when you have too high temperature, the growth rate decreases as temperature increases because now your species has too much energy. They readily dissolve from the sample surface, from the wafer surface, and makes the reaction harder to proceed. Right? So we want to operate in a window where the deposition rate is independent of temperature. Okay. So now I'll cover a bit on deposition parameters. So how do we quantify the characteristic of a deposition, right? One of important parameter is a side wall step coverage. So it tells you how well the side walls are being covered relative to your surface that is vertically exposed. So that is simply your side wall deposition thickness B divided by your surface deposition thickness A. So we can also consider side wall conformity. So that's like how uniform the film is being deposited on your side wall, and that can be given by the relationship of B over C. Okay, and we can also consider things like bottom stack coverage because in the bottom or trenches it tends to be harder to deposit, to cover, right? So we can consider the bottom stack coverage to be the coverage at the bottom divided by the coverage at the top. And so sometimes also we have this problem of overhang. So over here there'll be like overhang kind of structure. So we can quantify this by C minus B divided by B. So in a kind of a ratio. Okay. However, right, in addition to these kind of simple parameters that we can obtain after deposition, we can also characterize or model the deposition techniques by the use of physical parameters. So there are two important parameters: the sticking coefficient SC and the cosine input angle exponent N over here. So what is sticking coefficient SC? If SC equals to 1, the incoming species arrive on the surface and stick. Right? If your SC is less than 1, the incoming species land on the surface, they can move around, right? Bounce around or diffuse around, move around your surface before they settle into the final positions. So for example, if SC is 0.1, that means that your species can move around 10 times before sticking to a certain position. Okay. Then what about N, right? You can see how as N increases, right, the beam, right, your cosine theta to the power of N beam becomes more and more directional. Okay. So normally, right, if your ions are being accelerated, for example, in a PVD setup where you put a bias on your wafer to accelerate your incoming ions to deposit on your wafer, your N can be very much greater than 1 because your beam is forced by the potential difference to be more directional. Okay, so what is the effect of N and SC on your eventual deposition profile? So if your N becomes greater, we see that the deposition becomes more directional, so we are able to have a better coverage of the base over here, of the bottom. Okay, so it's able to better achieve your bottom coverage. And what happens if your SC increases? So that means it arrives and sticks more quickly, right? It doesn't move around so much. We see that because they arrive and stick, right? So the deposition also becomes more directional, and there's less overhang, and there's less sidewall coverage over here, because the species simply cannot arrive here at the first time in its first attempt. So if it arrives and then sticks, no species or hardly any species will be sticking on your sidewalls over here. Okay. So how does PVD and CVD systems compare in terms of these N and SC parameters? So let's talk about N first. So PVD systems generally have a more vertical arrival angle, right? Especially in a chamber that's low pressure, your species can travel a longer distance before colliding with other species. So it can basically travel at a straighter path and therefore arrive in a more directional fashion, and so N tends to be greater than 1. However, in CVD systems, you are pumping your reactant gases in. Your pressure is higher, there is some gas flows, so it is harder to achieve directional travel of your species without any collisions or being blown off course or collide, scatter off course. And so therefore, as a result, the arrival angle of your species is more directional. It's less directional. It's more isotropic. Yeah. Okay. And for SC, right? For SC, we see that PVD systems usually provide SC of 1 because there's little surface chemistry. There's no like surface diffusion and reaction and all that kind of thing. So atoms simply arrive and then they stick to their position in general. Okay. However, CVD systems are often involves adsorption chemical reaction step, and therefore your SC tends to be much less than 1. Your molecules, when they adsorb on your surface, because this adsorption, right, is not necessarily a very strong covalent kind of bonding, so your species can still undergo surface diffusion on your surface. And therefore we observe that for CVD systems, SC tends to be much less than 1, and the result, right, as you can see, is more conformal deposition, better coverage of side walls, for example, and can even cover under the overhang here. Okay. So this is the end of my video on CVD and ALD. So in the next video, I will cover ECP, electrochemical plating, as well as CMP, chemical mechanical planarization or polishing. Okay, thank you for watching. I hope you enjoyed this video.